Hello and welcome back. So we started discussing about homogeneous and heterogeneous nucleation in relation to grain refinement by melt inoculation. And in the last lecture, we talked about the Gibbs free energy change for nucleation.
Okay, so homogeneous nucleation is the process in which the nucleus forms without the aid of any surface or defect. Okay, so it's a unaided formation of the first nucleus of the product phase. So in case of the solidification, this is the liquid to solid transformation that we are talking about. So the parent phase is liquid and the product is the solid. Right. So in case of the homogeneous nucleation, it will occur in the parent phase without the aid of any surface or defect, as I said. So let's say this is the first solid particle which has formed from the liquid. Okay. So now depending on this size of the particle, it can be stable or unstable. So it has to reach a minimum size, a critical size for it to be stable and grow. And below that critical size, it is actually unstable and it can dissolve back into the liquid. Okay. So why is that so? You can understand if you consider the energies which are involved in this process. So here you can see that when the particle forms, the solid particle forms, it also creates an interface between the solid and the liquid. Okay. So a new surface is created. So you have the involvement of surface energy. And apart from that, you are creating a new volume, a new solid from the liquid. So the volume energy or the volume free energy is also changing. And this is basically the difference between the free energies of the product and the parent phase, which are solid and liquid respectively in this case, in case of solidification, right? So the volume free energy change is basically Gs minus Gl, where Gs is the free energy of the solid and Gl is the free energy of the liquid. So let us go back to this diagram now. You can see that at the melting point, these two free energies are equal and therefore delta G is 0, right? At the melting point. Now, if you look at this side below the melting point, you can see that the free energy of the solid, which is this one, is lower compared to that of the liquid. And therefore, delta G is negative. And the liquid will transform to solid as you pull it down below the equilibrium melting point. Okay, so this is the driving force for this transformation to occur and the first nucleus of the solid to form, right? But as I said before, when the nucleus is forming, you are also creating a new surface, an interface is created. So for that, you actually require a positive energy for creation of that surface. And that is exactly why you see these two contributions to the free energy change, okay, as you could see from this diagram now, okay. So this is the surface area contribution that is positive due to the creation of the new surface, right, this component over here. And this is the volume free energy change, which is essentially the difference of the free energies of the product and the parent phase, okay. So this is negative, as we have seen before, when the temperature is below the melting point. Right, and this solid curve that you see, that is the summation of these two, right? So now you can see, if you look at this total curve, the solid curve, for small values of R, the surface energy term is dominant, and that is why for small values of R, this curve will tend to follow the surface energy curve, okay, as you could see. But as R increases, the volume energy becomes more dominant, and when it goes beyond a particular size, this curve will tend to follow the volume energy curve, and as a result of that, it will come down beyond that critical size, okay. So what it essentially means is that below this critical size, the free energy is increasing, right, as you could see, because it is following this positive surface energy curve. So any size which is below this critical size will not be stable because the free energy is increasing, right? So that is what we call as the embryo. Which is not stable because it has not reached that critical size, and since below this the free energy increases, this is not going to be stable, right? On the other hand, when you cross this critical size, the free energy goes down, the free energy decreases, as you could see, right? So that is why beyond this critical size only, the nucleus will be stable, because now the transformation can take place, the transformation from liquid to solid, because free energy is now decreasing, right? So beyond this critical size, the nucleus will become stable and it will grow. Right? So this curve that you see, this basically represents the energy barrier for the nucleus. Right? The critical free energy change corresponding to the critical size, that is essentially the energy barrier for the nucleus. And we can derive this energy barrier by considering this particular equation over here, which shows these two contributions to the free energy change. This one, and this is what we have done in the previous class. If you differentiate this and then set this equal to 0 corresponding to that maximum, then you can derive the critical size R star and also the critical free energy change or the energy barrier. Right? So now let us come back to this, the heterogeneous nucleation case. So here the nucleation occurs on a surface which could be a defect or the mold wall in case of solidification, right? So this is the diagram which represents that. So this is the surface that we are talking about on which the nucleus is formed, right? So this could be a defect surface or the mold wall, as I said, okay? So that's what provides a substrate for the first nuclei to form from the liquid phase. And in this case, you will have to look at the surface energies also, because now, these interfaces are there. Apart from the solid liquid interface, there is an additional interface between that heterogeneous surface and the solid nucleus, and also between the surface and the liquid. Okay, so we are calling that surface on which the nucleus is forming as interface, indicated by I. Okay, so this is the interface, solid interface on which the solid nucleus is forming, right? And this is the corresponding interfacial energy, gamma IS. Okay. Similarly, this nucleating surface also has an interface with the liquid, so that is IL, and this is the corresponding interfacial energy. And this is the interface between the liquid and the solid, so the corresponding interfacial energy is this one, gamma SL. Okay, and this is the contact angle between the solid and the heterogeneous surface on which it is forming. Okay, theta is that contact angle. So theta can be found out if you take the balance of forces here. Okay, so from this equation, you can actually derive the expression for theta. Okay, so it's all about the surface energies here. Theta will also have a role to play on the free energy change. So now, if you look at the free energy change for this case, that is delta G heterogeneous, then here also there will be two contributions like how we had before. One, of course, coming from the volume, free energy change, and rest will come from all these surfaces, right? So here in this case, the nucleus which is forming is considered to be a spherical cap. So the area is derived based upon this assumption that the nucleus is in the shape of a spherical cap. Okay. So let's say the volume of that is that cap is Vc. Okay. And delta GV, of course, is the volume free energy change. So apart from this, you will have the surface energies. Where ASL is the area of this interface here, which is the solid liquid surface. Similarly, this is the area which is here, the heterogeneous surface and the solid, that particular interface. And you can also see the corresponding surface energies. Okay. And here you have another term which is negative. So this is the positive surface energy which is added to it. This is because of that creation of the new surface as we discussed before. But here this particular term you can see is negative, and this area is taken equal to the area of this interface between the solid and the heterogeneous surface on which it is forming. Okay, so this essentially means that the interface formed between the nucleating surface and the nucleus replaces an equivalent area of liquid and the surface interface. right? Which you can see from here, right? So this is the surface which is formed between the solid and the heterogeneous surface, right? And this is formed out of this particular surface, which is between the liquid and the heterogeneous surface, right? So an equivalent amount has been replaced when this interface forms, right? An equivalent area is replaced by formation of this interface between the solid and the heterogeneous surface. Now, considering the geometry of this, if you just do a simple geometrical analysis here, you would come across this particular expression for the free energy change. As I said, this can be easily derived by a simple geometry. I am not going to do this here. Maybe you can take this up as an assignment and you can do it yourself. So this particular term actually is similar to the homogeneous nucleation, if you recall, where this indicates a spherical nucleus that we considered before, right? So this SP indicates spherical shape for the nucleus, right? So this is nothing but delta G homogeneous, right? And therefore we can write that delta G heterogeneous is equal to delta G homogeneous multiplied by a factor which depends on the contact angle. So this one we can call as S theta, and therefore delta G heterogeneous becomes equal to delta G homogeneous into S theta, right? So if you plot this S theta as a function of theta, So here you can see when theta is equal to 0, S theta is also 0, right? So you have a point over here. And when theta is equal to 90 degrees, you can see that it is equal to 0.5. S theta is equal to 0.5 when theta is 90 degrees. Right? So it will vary like this. And as you could see, when the theta is equal to 180 degree, this becomes, S theta becomes 1. Right? So from here, we also need to calculate what is the energy barrier for the heterogeneous nucleation, that is the critical free energy change for the heterogeneous case. Okay. So following a similar approach of setting the d delta G by dr equal to 0, we can find out delta G star heterogeneous as this. This is delta G star homogeneous. We already know that. And therefore delta G star heterogeneous becomes this. Right? So from here you can see that the energy barrier for the heterogeneous case is much smaller compared to the homogeneous case for all practical values of theta. Okay? Because we have seen how S theta varies with theta. Okay? So now if you plot this delta G star heterogeneous by the delta G star homogeneous, as a function of theta, you would see that delta G heterogeneous is much smaller when theta is small, and then it goes to a value of 0.5 when theta is 90 degree, right? So for all practical values of theta, you can see that delta G star heterogeneous is always less than delta G star homogeneous, right? So for small values of theta, the energy barrier for the heterogeneous nucleation will be much lower compared to that for the homogeneous nucleation case. And that is why in nature generally the heterogeneous nucleation is always preferred, because the energy barrier for the heterogeneous nucleation is lower. Okay.
All right. With that, we come to the end of this lecture. Thank you for your attention.